Today, the Gaussian integral. Let's roll. Okay guys, so let's evaluate the integral from negative infinity up to infinity of e to the negative x squared dx, which is the famous, or maybe infamous Gaussian integral, which tells us the area under the Gauss curve, which describes the normal distribution in all of those weird statistics and economics textbooks, stuff like this, yeah? Okay, so why is this integral even interesting in the first place? Well, it's interesting because it's pretty hard to solve. It's actually impossible to solve, well, without using pretty neat tricks that I really like about this problem. That's why I wanted to show you guys. But it's impossible to solve by U substitution or maybe integration by parts. I mean, you can, I encourage you to pause the video now and try to play around with some substitutions, stuff like this. It's just that it just will not work. You're gonna use a neat trick that I would like to show you guys right now. Okay, so how to solve this integral? Well, I would like to first of all go on and denote our Gaussian integral from negative infinity up to infinity of e to the negative x squared dx as some kind of an I, where I will stand, I don't know, for integral, something like this. People just tend to denote integrals as I have no idea why, honestly. And I would like to go on and square both of those values. I would like to square both sides of this equality. Well, what is gonna be this integral squared gonna be equal? What's this integral squared gonna be equal to? It's gonna be equal to just, well, this integral by itself. I think it's pretty straightforward, as it's just as definition of squaring something. Okay, so I would like to write it as the Gaussian integral multiplied by the Gaussian integral itself once again. However, well, how can I rewrite this thing so it's, I don't know, easier or, well, who knows, to solve? Well, I'm thinking, what if I just were to switch this x right over here to some other variable, let's say a variable y, because it doesn't really make any difference for me to, rename some variables here. It's just gonna be a number anyways. I mean, in the very end, the answer is not gonna be any kind of a function like an antiderivative. It's gonna be just a number. So how I name those variables, well, it just doesn't make any difference for me. So let's go on and do this. I would like to now rewrite this product of those integrals as the product of, well, first of all, just the regular Gaussian integral in terms of x, but now I would like to multiply it by the, well, still pretty regular Gaussian integral, but in terms of y. And, well, why is it, why did I do that in the first place? Why is it an interesting way to rewrite this problem? Because now I can pretty much combine those integrals together, smash them each other, and just say that this entire thing is going to be equal to the integral from negative infinity to infinity of an integral from negative infinity to infinity of e to the negative x squared multiplied by e to the negative y squared dx dy. So just kind of, smash them together into a, well, single double integral, which is, well, we're kind of leaving the standard one variable calculus realm here. We're entering the world, the beautiful world of multivariable calculus, and what we're doing here is, well, we're not calculating the area under the curve anymore. We are calculating a volume on the surface. That's gonna be pretty much, that's gonna be pretty interesting, I think. And now it's, I think, an awesome moment to go on and introduce a beautiful trick there. So what I would like to do now is switch coordinate systems. I don't want to calculate this integral in the Cartesian coordinates. I would like to calculate in the polar coordinates. So, well, what the hell are polar coordinates in the first place? Well, you see, whenever we have the regular coordinate system, let's say I will have my plain old plane with the x-axis as the horizontal axis and with y-axis as the vertical axis, I think is how it's called. Well, if I were to denote some point on this plane, let's say the point 1, 1, what I do by introducing this kind of a point, though it's not really symmetric, but nobody cares about it, is I actually give an instruction on how to get to that point by moving by 1 in the positive x direction and then by 1 in the positive y direction. How I define points in polar coordinates is a little bit different. So what I will do is take myself this, how do you say it, horizontal line, and I would like to draw a circle. This is not a circle. Oh, now it's better. I would like to center this circle at the origin, yeah, something like this. So, or maybe let me draw the vertical line as well, so it's, you know, good for the reference. And I would like to now go on and once again denote the point 1, 1. This is the exact same point I pointed at right here in the in the Cartesian system, but now we're doing it in polar. So how I define points in the polar coordinate system is I give them 2 coordinates. The first coordinate, the r coordinate, is going to tell me how far this point lands here on the horizontal axis in either positive or negative direction, and then the second coordinate, theta, is going to tell me how much I have to rotate this point, by what angle I have to rotate this point, the angle theta, to get from the horizontal axis to the point I want to get. And so our point that I denoted here is going to have coordinates square root of 2 and pi, no, not pi over 2, and pi over 4. Well, it's gonna tell us that we have to go by a square root of 2 here in the positive x direction, and then take this point we have here on the horizontal axis and rotate it with respect to the origin by an angle of pi over 4. So by it's 45 degrees? Yeah, it's 45 degrees. But now, well, as I already said, this is the exact same point as in our, well, regular plane or plane. That's going to be our point 1, 1. And so what we can actually do here is kind of interpret this thing as an emulation of our instruction we gave to go by 1 in the positive x direction and then by 1 in the positive y direction in the Cartesian system. We can just, well, do the same thing here and draw a triangle such that one vertex of this triangle is gonna be the origin, the O point. The second one is gonna lie here somewhere on the horizontal axis, at a distance of a square root away from the origin, but this doesn't really matter. And then the third vertex is gonna be our point, the one we denoted in both of those coordinate systems. And once again, I have to point it out, those 2 points are the same. Those are the same points. Yeah, they have the same distance from the origin. They are, well, placed the same with respect to the origin. They're just described differently. What we did here is we described the way to get to that point from the origin differently to the way we described how to get to that point from the origin in the polar coordinates. And so what we can do here is, well, actually interpret this entire thing as... Okay, so okay guys, so I could kind of cut that because my camera died, but it doesn't really matter, we can move forward. So we can interpret this triangle right here as, well, a triangle that's gonna have the angle theta here next to the origin, and where this side right there is gonna tell us how much we would have to move upwards in the positive y direction in the Cartesian system, and this guy right over here is gonna tell us, this side right over here, its length is gonna tell us how much we would have to move in the positive x direction in the Cartesian system. And so what we'll actually get, if this is our r, this is the oh man, the distance we have to travel from the origin to that point and then rotate that point by the angle of theta, is gonna be the, I think it's called the hypotenuse. Please can't let it be called the hypotenuse. I don't want to recall this thing again. So we'll actually have a pretty nice conversion formulas for switching from the Cartesian to the polar coordinates. That is, that x is going to be equal to r cosine theta, and that y is going to be equal to r sine theta. Well, you can see it from just doing a little bit of trigonometry here, because, well, the side that is going to have the length of y here divided by r is going to be equal to the sine of theta, and the side here that's gonna describe how much we have to travel in the positive x direction is gonna be equal to cosine of theta when divided by r. Awesome. So, well, we can do the same, we can apply those formulas right now to our integrals to change those bases, However, to change those coordinate systems. However, there's a problem with those bounds of integration, because what the hell would that mean for us to integrate from negative infinity to infinity on a grid that looks like this? And you don't really have two axes that, well, cross at a right angle. You just have a bunch of circles with certain radiuses. It's weird. Well, there is a nice method to write it down. I mean, you can interpret this as the integral from 0 to double pi of integral from 0 to infinity of e to the negative x squared, negative x squared. That's gonna be now the negative r squared cosine squared x multiplied by e to the negative r squared sine x times r times dr d theta. One more thing I have to point out here, this r right over here appeared, actually had to appear, this a requirement, though I'm not gonna be really diving into why this appeared here, because I would really like to make a video in the future about how to, well, switch coordinate systems. That's gonna be a little bit more into depth, not, you know, my fast and furious explanation I try to give today. So I'm just gonna leave this with a question mark, but, well, there's a fact, it had to appear here. Awesome. Well, so why those bounds of integration do even make any sense? Because you see, when I had those two negative infinities and those two infinities in those original bounds of integration, what I actually did is I said that I'm gonna cover all of the x's, all of the y's from negative infinity up to infinity. I'm gonna cover all of the x's from negative infinity to up to infinity. Yeah, so I'm gonna take all of the x's, all of the y's, and just combine them into pairs. So what I'm doing here is I'm saying I'm gonna take all of the thetas, that are there. Yeah, because, well, as you can see, theta can only be between 0 and double pi, yeah? Only between 0 and 360 degrees. And also I say I'm gonna take all of the r's there are, yeah? All of the r's. And why am I taking r's to be between 0 and positive infinity and not negative infinity and positive infinity? Because this point right there corresponds to this point right here, but, you know, with the angle of theta just being a pi larger. And so as I'm taking those thetas to be from 0 to double pi, I'm actually pretty much taking those r's to be from negative infinity to positive infinity. It doesn't really matter for me. Okay, so what can we do here right now? I forgot to put a square here next to the sign. So now we can just, well, kind of use the trig identities, which is going to be pretty lovely here, because as we can see, this negative r squared, actually let's say this product of those two exponentials we can write as just a single exponential to the power of negative r squared cosine squared x minus r squared sine squared x. But that thing is just equal to e to the power of negative r squared. And then we're going to multiply this entire thing by cosine squared plus sine squared x. And, well, what did I do here? I just factor out this negative r from the from cosine squared and sine squared, but, well, by trig identities we know that this sum of cosine and sine both squared is equal to just a 1, and so this entire thing is going to be just equal to e to the power of r of negative r squared. And so we can go on and nicely rewrite this entire thing as the integral from 0 to double pi of integral from 0 to infinity of e to the power of negative r squared, sorry, I forgot, r dr d theta. And, well, why is this thing better? Why are we better off now than we were at the very beginning of the problem? I mean, we still have the e to the negative r squared, for God's sake, but now we have this mysterious r right over there. And why is it awesome? In the original problem, we couldn't really use the u substitution of, let's say, u being equal to negative x squared, and that's because if we did, well, we wouldn't have any x right here to cover the gap that would definitely emerge when trying to derive the du formula, because, well, du would be equal dx would be equal to w du, yeah? But now we can definitely do it. We can evaluate this integral right over here. Let's just take the antiderivative of this guy, so e to the negative r squared times r dr. And I would like to make a substitution, the substitution of, well, r squared being equal to u, and so double r dr being equal to du. I'm not changing bounds of integration because it's an indefinite integral. I'm just trying to get the antiderivative of e to the negative r squared times r. And so this thing, or maybe I will do it in yellow, by our substitution is going to be equal to the antiderivative of e to the negative u, to actually 1/2 of the integral, from e to the power of negative u du. But, well, this thing is just negative 1/2 e to the negative u plus a constant, but we won't really care about this constant when we plug this thing here into a definite integral. And so we can just go on and rewrite this entire thing as the integral from 0 to double pi of negative 1/2 e to the negative, let's say, r, because now we can just, switch the variables again, negative r in the bounds of 0 and infinity, and then the theta. But a nice thing is that as r approaches infinity, this thing will approach 0, and so this entire thing is just gonna be negative 1/2 e to the 0. That's gonna be negative and negative half, so that's gonna give us the integral from 0 to double pi of just a half d theta. And, well, that thing is just gonna give us theta over 2 evaluated between 0 and double pi, which is gonna be equal to just a pi. And so we see that our original integral squared is equal to pi, and so this means that our original integral, not squared anymore, is gonna be equal to the square root of pi. And so we see that this is the answer to our problem. The integral from negative infinity up to infinity of e to the negative x squared dx is gonna be equal to, let me clear out those arrows, square root of pi. Oh man. So once again, what did we do here? We denoted our integral as some kind of an I. We squared that I. We noticed that whenever we square something, we're kind of just multiplying it by itself, double 2 times. And so what we did is just we wrote down those two integrals, those two Gaussian integrals multiplied together. We changed the variable x in one of those to a y. So what we did then is we combined those two integrals. We created a single double integral, with respect to those two variables. Then what we did is we changed coordinate systems after a brief introduction to what polar coordinates are. I'm actually gonna do a long form video in the future about it, but, well, yeah. Today it's just kind of hard to be fast because, a short video. I mean, it was supposed to be a short video. It's 15 minutes long or something, so it's not so bad. Then what we did is we used some trig identities after summing in x equal to r cosine theta and y equal to r sine theta, stuff like this. The formulas for changing the coordinates, the x and y to the polar coordinates we derived from the brief introduction to those coordinates. And so we got, after also, having to change those bounds on integration, that this entire thing was equal to the integral from 0 to double pi of the integral from 0 to infinity of e to the power of negative r squared times r dr d theta. When what we did is we just kind of evaluated the antiderivative of e to the negative r squared times r dr, which was equal to negative 1/2 of e to the negative u, and then we just evaluated it within bounds of 0 and infinity, and then take the integral from 0 to double the pi, the theta of that thing, and the final result was pi. However, taking the square root of the final result will give us the final result, so what the Gaussian integral is actually equal to, and that was the square root of pi, which is a pretty famous result. Okay, so I really hope you guys enjoyed this video. Well, if you did, like, subscribe, and see you in the next one.